Welcome back, everyone. I'm here on page 2 of the Chapter 7 lecture note outline packet. So make sure you have that open so you can follow along, and let's go ahead and get started. So in the last lesson, we learned if we were given a reaction, say A and B goes to C, we learned that we can take the mass of A, in grams, or the mass of B in grams, and we can find out the mass of C in grams, or vice versa. And we learned how to do this by using the conversion factors built into the chemical equation. And it looks something like this. We found that if we wanted to know the mass of C, but we were given the mass of A, we would first convert the mass of A into the moles of A, and then the moles of A into the moles of C, and then we could find the mass of C from the moles of C. And we looked at the different conversion factors for all of these steps. So for example, when we wanted to go from the mass of A to the moles of A, we saw that we would use the molar mass. If we wanted to go from the moles of A or the moles of B to the moles of C, we would use the coefficients from the reaction equation. And then if we wanted to go from the moles of C to the mass of C, we would use the molar mass for C. Now, these are the different steps that we learned how to do. What we're going to look at today is an extension of this type of work, something called limiting reactant problems. Now, the problems we've looked at so far assumed we had enough of A or of B to assume all of it would have reacted. Now, when we have multiple reactants, it is possible that, in fact, not just possible, but likely that we don't have enough of both to completely convert all of the reactants into products. One of the reactants, it turns out, is probably limited. And so for that reason, we call these limiting reactant problems. Okay, limiting reactant is a reactant or starting material that limits the amount of product that is possible. It is the reactant that is capable of producing the least amount of product. So here's a simple analogy. It turns out a recipe for pound cake is if you have 1 pound each of flour, sugar, butter, and eggs, you can make a pound cake. So let's assume we had 10 pounds of each. We can make 10 cakes. Now, what if we didn't have 10 pounds of each? What if we had, say, 15 pounds of flour, 8 pounds of sugar, 4 pounds of butter, and 50 pounds of eggs? How many cakes could we make? Could we make 50 cakes because we had 50 pounds of eggs? Well, no. That's because we are limited by the amount of butter that we have. Notice that the limiting reactant in this case is butter because that is the ingredient that we would run out of first. So while in this first example, when we had 10 pounds of each, we don't have a limiting reactant because none of them would run out earlier than the others. The second example, we do have a limiting reactant. The limiting reactant is butter because that's the ingredient that we would run out of first. It's also the ingredient that would make the least amount of product, or in this case, cakes. So butter would run out first, therefore it's the limiting reactant. And if you think about it, the maximum number of cakes we can make is going to be based on that limiting reactant. We call this the maximum theoretical yield, or the theoretical yield for short. And in this example, it's pretty easy to see what the maximum yield is because it's based on that 4 pounds of butter. We see that the maximum number of cakes we can make is 4, and that's what we're going to call our theoretical yield. So it's fairly straightforward to see how this process works with an example like this where we have a recipe. What about with chemistry where we don't have a recipe like we would for a cake? Well, it turns out we do actually have a recipe, and that's the chemical reaction. So what we're going to learn how to do is, given a chemical reaction and the quantities of reactants that we have available, establish which one of the reactants is the limiting reactant, and based on that, determine the maximum theoretical yield. So let's go to the next page so we can start to learn how to actually do this. So here on page 3 of the Chapter 7 lecture note outline, we're going to start to learn how to actually do limiting reactant type problems. So I have a chemistry example up here. Before we look at that example, though, let's look at the step-by-step outline for how we actually solve these types of problems, taking a systematic approach. I've outlined a 3-step approach to solving limiting reactant problems, and it turns out you already know how to do each of these steps. It's just seeing how to apply them into these particular types of problems. That's probably new. So what do we do? First thing that we're going to do is we read through whatever problem we're looking at, and if there isn't a balanced chemical reaction already present, that's the first step. We're going to write out a balanced chemical reaction for the problem. Now in the second step, we're going to determine the limiting reactant. And to do this, what we're going to do is look at the mass of each reactant that we're given and determine how much product is formed from that mass of reactant. So we go through the process we've already seen, where we take the grams of the reactant, convert it into moles of reactant, and then turn that into the moles of product. The limiting reactant is simply the reactant that produces less moles of the product than the other. Once the limiting reactant has been established, it's an easy matter to find out how much product is formed from that limiting reactant. You simply convert the moles of product that would be formed by the limiting reactant into the grams of product using the molar mass of that material. So let's apply this method to this example problem that I have here. When an aqueous silver nitrate solution is mixed with an aqueous solution of sodium chloride, solid silver chloride precipitates from the solution. And the question is how much silver chloride would be formed from 100 grams of silver nitrate that is mixed with 100 grams of sodium chloride? And what is the limiting reactant? So we're given the mass of two different starting materials, and we're being asked to determine the mass of the product. This is obviously a limiting reactant problem, and we need to start by writing out the balanced chemical reaction. So I want you to go ahead and give that a shot. Try to write out the reaction equation and then balance it. So this is an example of a double displacement reaction where we have two aqueous salts. One of the salts, silver nitrate, is mixed with the other salt, which is aqueous sodium chloride, and then we have the precipitate, which is silver chloride. The other product we have is sodium nitrate, and that is soluble in water. Once we have the equation written, we notice that it's already balanced as it is. We don't have to change the coefficients for any of the reactants or any of the products because all of the atoms on the left add up to the same number and type of atoms on the right. So it's already balanced. Now what we're going to do is try to determine which of the reactants on the left, silver nitrate or sodium chloride, is the limiting reactant. And remember, the limiting reactant is the one that produces the least number of moles of product. So let's go ahead and determine the limiting reactant. To determine the limiting reactant, for each of the reactants, we are going to convert the grams of the reactant into the moles of the reactant. And to do this, we're going to use the molar mass of the reactant. Once we have the moles of the reactant, we can convert that into the moles of product using the coefficients from the balanced chemical reaction. So in this example, we have 100 grams each of silver nitrate and sodium chloride, and we're going to convert that 100 grams of each of those reactants into the moles of the reactant. We're going to use the molar mass for each one. Once we have the moles of the reactant, we can convert those into the moles of the product using the coefficients from our reaction equation that we wrote up here in step 1. So let's get started with one of our reactants. How about we start with silver nitrate? Now, because we're going to need the molar mass for both of our reactants, I'm going to write them here in the beginning, and we're going to use those throughout the problem. So to find out if silver nitrate is the limiting reactant, we're going to start by converting the mass of silver nitrate into the moles of silver nitrate. So I'll show that here in my first conversion factor, that the unit on the top will be moles of silver nitrate. All right, now the second step is we're going to convert moles of silver nitrate into the moles of the product we're interested in, which happens to be silver chloride. So that will be my second conversion factor, where moles of silver chloride is the top unit. Once I've done this conversion, I'll be left with the number of moles of silver chloride that can be formed from 100 grams of silver nitrate using this reaction. So now we just need to complete the conversion factors. The first conversion factor, where we convert from grams of silver nitrate into moles of silver nitrate, is the molar mass for silver nitrate. My molar mass for silver nitrate is indicated up here. For each mole of silver nitrate, we have 169.87 grams. In the second step, I'm converting from moles of silver nitrate into moles of silver chloride. So my conversion factor needs to have the coefficients in front of each of these, and these are from the balanced chemical reaction. Notice up here in the chemical reaction, I'm going to put the little coefficient lines in front of each. We have a balanced chemical reaction when each of these coefficients is the number 1. So if I have number 1 in front of silver chloride and 1 in front of moles of silver nitrate, those are the correct conversion factors. Now, once I go through the entire calculation, I get 0.5887, that's 4 significant figures. And again, that's the moles of silver chloride that could be formed from 100 grams of silver nitrate. But we still have to answer the question of the other reactant, right? The other reactant we have 100 grams of is sodium chloride. So we need to determine how many moles of product could be formed from that reactant also. So we follow the same process for the other reactant. We start with our 100 grams of sodium chloride, and we're going to need to convert that first into the moles of sodium chloride. So my first conversion factor will have to have moles of sodium chloride on the top. Now in the second step, I'm going to convert from moles of sodium chloride into moles of the product, which is silver chloride. So my second conversion factor will have moles of silver chloride on the top. Now, going through these steps, I will be left with the moles of silver chloride that could be formed from 100 grams of this second starting material, which is sodium chloride. Now we just need to go in and complete our conversion factors for each of the steps. The first conversion factor is molar mass. We're going from grams of sodium chloride into moles of sodium chloride. So we need to look at the molar mass for this, which is shown up here above, where we have 1 mole of sodium chloride is 58.44 grams. So let's fill those numbers in. Now the second conversion factor, where we're going from moles of sodium chloride into moles of silver chloride, that's derived from the coefficients in the balanced chemical equation. So we're going to have our 2 blank spots right in front of each of these units. We're going to look to the equation, the reaction equation, to find the coefficients, which for silver chloride is 1 and for sodium chloride is 1. So we put the values 1 and 1. Now going through the steps of doing the calculation, you end up with 1.711 moles of silver chloride, and that's again from 100 grams of sodium chloride. So let's look at these 2 values, these 2 results, and determine which one of them indicates the limiting reactant. Now remember, the limiting reactant is just the reactant which produces the least amount of moles of product. So if we compare these 2 mole results for silver chloride, that's our product, which one of them is less? Well, that's correct. This one is less. So it seems that from 100 grams of silver nitrate, we can only make 0.5887 moles of silver chloride. That would mean that silver nitrate is our limiting reactant rather than sodium chloride. Because with sodium chloride, we can make more than 3 times as much, 1.711 moles. There's no way we'll ever be able to make that much silver chloride because we would run out of silver nitrate once we hit 0.5887 moles. So we've established that silver nitrate is our limiting reactant. So I'm going to put a little star there and then say LR to indicate that. Now, a good question to ask yourself is why? Why is silver nitrate the limiting reactant here? We're starting with the same amount of each, right? 100 grams of silver nitrate, 100 grams of sodium chloride, and the reaction consumes them at an equal rate, right? And we only need one of this and one of this to produce one product. So if they're consumed at the same rate and we're starting with the same mass, why is it that we're going to run out of silver nitrate first? Well, the reason why we run out of silver nitrate first is because we have only 1/3 as many silver nitrate ions as we do sodium chloride. Why is that? Well, take a look at the molar mass of silver nitrate. It's more than 3 times as much as it is for sodium chloride. So if we're taking the same number, 100 grams, and we're dividing it by a larger number rather than a smaller number, that means our limiting reactant is silver nitrate because we simply have less of them. So that's why we're getting this difference. There's 3 times as many moles produced from sodium chloride as there are from silver nitrate, simply because of the differences in the molar masses here. So now that we know how to establish the limiting reactant, we're going to go to the next page and learn how to convert these molar quantities into an amount we would measure in the lab, mass. So we'll learn how to determine the maximum theoretical yield, as well as determine the percent yield, which is a measure of the efficiency of a reaction. So let's continue on the next page. So here on page 4 of the lecture note outline for chapter 7, we see this next example, which brings mass into this type of problem that we're working on, these limiting reactant problems. So if we read through this, it says the rocket fuel hydrazine, which is N2H4, the molar mass is given to us for it. This fuel, hydrazine, can be prepared from ammonia gas and hydrogen peroxide. Again, both the molar masses are included there for us. Water is the only byproduct of this reaction. Now, if we had 320 grams of ammonia and 450 grams of hydrogen peroxide, those are our two reactants, what's the maximum amount of hydrazine fuel that you could produce? So this is another limiting reactant problem, except instead of just getting to the limiting reactant, we actually want to know what's the maximum amount in grams that we could produce. So I'm going to write grams here just to make sure that's emphasized, that what we're looking for here is grams. It doesn't say that, it should, but basically we're looking for the mass. So how do we go about doing this? Well, we're going to do exactly the same thing we did before, except instead of stopping at the moles of product from each of the limiting reactants, we're going to actually continue and convert those into grams. So let me show you how to do this. The first step is, of course, write out a balanced chemical reaction. So I want you to pause the video and see if you can write the reaction equation for this process, and then check yourself against the one that I show here. Okay, so first step, let's write out the equation. The equation for this is pretty straightforward. We're told that we're using ammonia gas and hydrogen peroxide as the reactants. So ammonia, again, the formula for that is NH3, and we know that's indicated here as a gas. Then we get H2O2, that's hydrogen peroxide. Now, the state isn't indicated here. That's not really important for this reaction, so I'll just leave it off. Then we're preparing hydrazine. That's one of the products that we have. And it turns out hydrazine is a liquid. Again, that's not really important for this reaction, but I'll just put it in there to show you. And the other product for this, the byproduct, is water, so H2O, and that's a liquid. Now that we have the equation written, we still need to go ahead and balance it. So once you have this equation down, go ahead and see if you can figure out the coefficients for each of these. So when you first start balancing it, the first thing that you probably will notice is that nitrogen is unbalanced right at the beginning. And we can start by balancing nitrogen first. So if we have 2 nitrogen atoms in the product, we should have 2 in the starting material as well. So let's go ahead and balance ammonia with hydrazine. Now, because there are so many hydrogen atoms all over the place, it might be best to save that for later and deal with the easier atoms first. So notice that we have 2 oxygen atoms over here in hydrogen peroxide. So we have 2 there, but there's only 1 over here in water. So we can fix that right off the bat by putting a 2 in front of water. Now, if we look, the only thing left to balance is hydrogen. So let's add up all of the hydrogen atoms on the left and all of the hydrogen atoms on the right and see if we have a balanced situation. So we have 6 because of ammonia, right? The 2 times 3 is 6. And then we add 2 to that if there's a 1 here. So it would be 6, 7, and 8. That's on the left. Now, if we go over here on the right, we've got 4. That's assuming there's a 1 here. So we would have 4 hydrogen atoms. Plus another 4, and that's 8. So if the coefficients are 1 and 1 here, hydrogen is also balanced. So this is the balanced chemical equation. Hopefully you got that right. Let's go to step 2. So in step 2, we're going to follow the same basic process that we followed previously. For each of the reactants that we have to consider, we're going to find out how much product each one could make. Now, instead of finding out how many moles each one could make, instead, we're just going to find out the mass that each one could make. And whichever one produces the least amount of mass, that would be our maximum yield. The step-by-step process for actually doing this looks very much the same as it did before. We're going to start with our mass of a reactant, so I'll call that R. So we start off with grams of R, and we convert that into moles of R. Once we have moles of R, we can convert that into the moles of the product, which I'll call P. So we go from moles of R to moles of P. Now that we have the moles of P, we just convert that into the mass of P. And we've then converted the grams of R into the grams of P. Now the conversion factors that we use at each step are pretty much the same as before. We're using in the first step the molar mass of R to go from grams of R to moles of R. Then from moles of R to moles of P, we just use the coefficients from the balanced chemical reaction. And then to go from moles of P into the grams of P, of course, we use the molar mass of P. So we have 3 steps here instead of the 2 that we had on the previous page. So go ahead and give this a try. Apply this method to each of our starting materials and determine the amount of hydrazine that each one could produce. From that information, you'll determine 2 things. You'll be able to determine which reactant is the limiting reactant, and you'll also be able to determine the maximum yield of hydrazine. So here's what the setup looks like. We're going to start with the mass of each of our reactants. We're told that we have 320 grams of ammonia, and notice I put a decimal place next to the 0 in 320. It should have 3 significant figures. I must have just left that off in the problem. We also are told that we have 450 grams of hydrogen peroxide. Notice also I've placed a decimal place there as well to give it 3 significant figures. So what we're going to do is convert for each of these masses, we're going to convert them to the grams of the product. This will require 3 conversion factors, or 3 steps. So for ammonia, in the first step, we're converting from grams of ammonia into moles of ammonia. So we'll have moles of ammonia in the top position of that conversion factor. Then we're going from moles of ammonia into moles of hydrazine, so that would be the unit in the top of the second conversion factor. And then we're going into grams of hydrazine, so we'll have grams of N2H4 in the top position there. We can do the same process for hydrogen peroxide below, except we're going from grams of hydrogen peroxide into moles of hydrogen peroxide instead of moles of ammonia, of course. And then the next 2 steps are exactly the same as the 2 above it. So if we look at this, in each case, we're converting the grams of whichever reactant we're looking at into the grams of hydrazine that it would produce. So in the top case, we'll have grams of hydrazine that could be produced from 320 grams of ammonia. And in the second case, we're getting grams of hydrazine that could be produced from 450 grams of hydrogen peroxide. Now, all that's left for us to do is to complete the conversion factors and then do the calculation. Let's see how that works. So in this first step, I'm converting from grams of ammonia into moles of ammonia. So I need to use the molar mass for ammonia, which is given here in the problem. We see that 1 mole of ammonia is equivalent to 17.03 grams. In the second step, we're converting from moles of ammonia into moles of hydrazine. So we need to use the conversion factors that are derived from the coefficients in the balanced chemical equation. If we take a look at the equation, we see that the ratio of moles of hydrazine and moles of ammonia is given as 1 to 2. Now, in the last step of the conversion, we're going from moles of hydrazine into grams of hydrazine. So for this conversion factor, we need to use the molar mass. The molar mass is given to us above in the problem, and it indicates that there are 32.0452 grams for every mole of hydrazine. So let's put those values in here. Now, if we do this calculation, we end up getting 301 grams of hydrazine that could be produced from 320 grams of ammonia. In the first step, we're using the molar mass of hydrogen peroxide, which is given to us above in the problem. In the second step, we're converting from moles of hydrogen peroxide into moles of hydrazine. And for that reason, we need to use the coefficients from the balanced chemical reaction in our conversion factor. So if we take a look at the top value here, we're looking for the coefficient for the moles of hydrazine, which equals 1. And at the bottom, we have moles of hydrogen peroxide, and that coefficient is also 1. So that's our conversion factor for the second step. Let's go to the third step. Here we're converting from moles of hydrazine into grams of hydrazine. So again, we need to use the molar mass here. The molar mass is given to us in the problem. We have 32.0452 grams of hydrazine for every mole of hydrazine. Now, if you work through the calculation, you will calculate 423.94 grams of hydrazine produced from 450 grams of hydrogen peroxide. We only have three significant figures, so we end up rounding that to 424 grams. And now we can compare the two values. These are the masses we would expect to be produced of hydrazine from their respective starting materials. And notice that from ammonia, we produce less hydrazine. So ammonia would in fact be our limiting reactant, and our maximum theoretical yield would therefore be 301 grams of hydrazine. So if you got that right, great job. Let's go on to the next section here, which is percent yield in Part D. Again, this is page 4 of the lecture note outline packet. So it turns out that this maximum yield that we can express based on limiting reactants is also a good way for us to measure the efficiency of a reaction. Right? Since we've determined the maximum yield that a reaction can have, we can then actually go and run the reaction and compare what we actually isolate from the reaction with the maximum theoretical possible. This is a measure, again, of the efficiency of a reaction, and it's called the percent yield. To determine a percent yield, we need to know two things. The first thing we need to know is what was the actual yield of the reaction when it was run. This is called the actual yield for a reaction, and it is determined experimentally. For that reason, we will have to provide you with this value if we want you to be able to determine percent yields. The other thing you need to know to determine a percent yield is the maximum theoretical yield. Now, this is something that you can calculate before ever having to actually run the experiment yourself. So we need to know these two things, the actual yield and the maximum theoretical yield. Once we have the actual yield and the maximum theoretical yield, we divide the actual by the theoretical, and then we multiply it by 100 to give a percentage. So, for example, back with our pound cake analogy, if we had 5 pounds of flour, 3 pounds of milk, and 6 pounds of butter, and 4 eggs, and 2 cakes were made, what is the percent yield? Well, what we do in these types of problems is first determine what the limiting reactant is. And if we look at this, we see that milk is the limiting reactant with only 3 pounds of it. So from that information, from the limiting reactant, we then determine the maximum theoretical yield. Again, that's the yield that would be based on the limiting reactant quantity. So in this case, we have the maximum yield being 3 cakes possible. In the third step, we actually calculate the percent yield. Again, this is the actual yield divided by the theoretical yield and then multiplied by 100 to give a percentage. In this case, we have the actual yield of 2 cakes, and we're dividing that by 3 cakes. So it's 2 divided by 3, and then multiply that by 100. So we see it's a percent yield of 66%, approximately. So let's go to the next page where we will look at a real example and see if we can determine the percent yield. So here on page 5 of the Chapter 7 lecture note outline, we see an example allowing us to practice the percent yield calculation. The example reads, when 9.25 grams of hydrogen gas are allowed to react with an excess of nitrogen gas, 15.1 grams of ammonia are formed. What is the percent yield for this reaction? So the first thing we need to do is establish which reactant is the limiting reactant. Now, if we read through this problem, we see that the word excess is used to describe nitrogen gas. So if we have two reactants, hydrogen gas and nitrogen gas, and we're told that nitrogen gas is in excess, that means that that one is not the limiting reactant, and the only other reactant we have is hydrogen. So therefore, hydrogen gas must be the limiting reactant. So let's just write that down. Now, once we've established the limiting reactant, we need to determine the theoretical yield. The theoretical yield is the mass of product that is made from the limiting reactant. So what we're going to do is convert the grams of the limiting reactant into the grams of the product. that will be the maximum theoretical yield. Now I'm going to show you how to do that for this problem, but recognize this is exactly the same as what we were doing on the previous few pages. So we'll start by writing out a balanced chemical reaction, and then we'll do the conversion from grams of hydrogen into grams of ammonia. Here's what the reaction looks like. We have hydrogen gas, that's H subscript 2, and we have nitrogen gas, that's N subscript 2. Those are both diatomic elements, that's why they have the subscript 2. The product is ammonia, which has the formula NH3. Notice that we have 2 atoms of nitrogen on the left, but ammonia only has 1 nitrogen in it. This is where the 2 coefficient comes from in front of ammonia. To balance out the hydrogens, then we have the 3 coefficient in front of hydrogen gas. Now what we're going to do is convert the grams of hydrogen. We have 9.25 of them. We're going to convert those into the product, the grams of ammonia. So we're going to have 3 steps to do this, the same 3 steps that we saw on the previous page. The first step is we're going to convert from grams of hydrogen into moles of hydrogen. Then we're going to convert moles of hydrogen into moles of ammonia. Then we're going to convert into grams of ammonia from moles of ammonia. Doing this calculation will then give me the grams of ammonia that I can produce from the amount of hydrogen gas available. This is the maximum theoretical yield possible. Now let's fill in the conversion factors for each of the 3 steps. In the first step, I'm using the molar mass of hydrogen, which is 2.016 grams. I got that by adding up 2 hydrogen atomic mass units. Then in the second step, I'm using the coefficients 2 and 3. That's from the balanced chemical reaction that we wrote in the previous step. The last step of the conversion is this conversion from moles of ammonia into grams of ammonia. This value can be determined by adding up all of the atomic mass units for nitrogen and hydrogen. I've also shown this molar mass on the previous page. So if you run this through your calculator, you will get a calculated value of 52.095486 and some other digits. Now we only have 3 significant figures, so I'm going to round this to 52.1 grams of ammonia. That's how much ammonia we could produce at maximum if we use 9.25 grams of hydrogen. Now, let me bring something up real quick. Why is that such a large number? It's 52 grams of ammonia, but we're only using 9.25 grams of hydrogen. Well, that's because most of the mass of ammonia is not actually from hydrogen gas. It's actually because of the nitrogen. Now, notice that we have nitrogen in excess here. We're not limited by the amount of nitrogen gas we have. So therefore, most of the mass is being introduced by the non-limiting reactant. Now, we have one more step to complete this problem, and that is to determine the percent yield. We're going to divide the actual yield, which is given to us here as 15.1 grams of ammonia. We're going to divide that by the theoretical yield, which is 52.1, and then we will multiply that by 100 to get the percent yield. And if your calculation gave you 29.0%, great job. You determined the percent yield for this reaction. All right, so let's go to the last page in this lecture note outline and take a look at what we have next. Now here on page 6 of the lecture note outline for chapter 7, this is the last page, we have a problem that I think would make really good sense to use during the review. You're going to go through this problem and see if you can determine the isolated yield or the mass recovered of silver in this reaction. So go through and see if you can work through all of the different steps that I just showed you on the previous pages, and then we'll go through this during the review session before the next exam. With that, I'll end this lecture, and let me know if you have any questions. I will see you soon. Take care.